Okay, previously we talked about outer measures. The outer measure is defined in a very intuitive way, but the problem with the outer measure is that it is not countably additive. By countably additive, we mean that we have a collection of sets, the case from 1 to n, case from to infinity. And all those cases are mutually disjoint. By this, we mean that you pick up any two of them, they are not overlapping. They do not overlap. Okay, so in this case, we would hope that the outer measure of the union of these sets is equal to the sum of the outer measure of them. Okay, unfortunately, this does not hold in general, and that's the problem with outer measure. Although it's defined very nice, intuitively, it's just that there are cases that where you have mutually disjoint sets, case, but the union doesn't have the same measure as the sum of the individual measures. Okay, so this is the problem we're going to overcome, and in this sense, we are going to restrict ourselves to the nicer sets, which are called measurable. Okay, so here's the definition for measurable sets. Okay, a set E is called measurable if for any set T there is the outer measure of T equals to the outer measure of T intersection of T and E plus the outer measure of T intersection of T and the E complement. Okay? In this case, we call T a test set. Okay, so what this definition says is if E is a countable, if E is measurable, if the decomposition of any test set, so you know that for any test, for any T, say this is the E, and it doesn't matter what this T is, the outer measure of T is the same as the sum of this part, which is the intersection of T and E, plus the outer measure of this part. Okay, so that is the these two terms. So this first term gives the measure of this area, outer measure of this area, and this term gives the outer measure of this area. So if for any T, the outer measure of the T is equal to the sum of the measures like this, then we can call E a measurable set. So here T can be any set. So this need to hold for any T. It doesn't matter what this T is. Okay, so this is in this case we call the E a measurable set. Okay, so it seems like the T can be used to measure any other sets in the sense that if you partition the set T into two parts, two disjoint parts, this and then this, the outer measure has this additivity. Okay, can be discrete, can be separated into this two. Okay. So actually, due to the property of outer measure we showed before, if you have two sets, remember that if you have two sets A and B, then the union of the 2 has an outer measure less than or equal to the outer measure of individual of them and take the sum. So because of this, we always have this side less than or equal to this, because t can always be written as the union of these two, right? So this side, left-hand side, is always less than or equal to the right-hand side. The key is that if we can show this for any set t, if we can show this holds for any t, then the E is measurable. Okay, so in the future, if you want to show a set is measurable, a set E is measurable, you just need to show this inequality here. Just show this for any t. Okay, so now we before continue, I'll give a name for this. So or the collection of all measurable sets is denoted by M of Rn. So the collection of all such measurable sets E is denoted by that. And sometimes it's just denoted by M. Okay. Okay, so now let's continue the property of these measures. Okay, so as you can see, this gives us a more restrictive definition because so for any set we can define the outer measure, but not all the sets are measurable. So only the sets that satisfy this equation for all the t are called measurable. So now let's study several special cases for which we know that set must be measurable. So the first example is all the outer measure zero sets are measurable. Okay. If the outer measure of a set is 0, then E is measurable. So in other words, we can just write in this way. Okay, so as we said, this is a shortcut for this. Since we're always considering in a generic n-dimensional Euclidean space, so we just need to write this M here. This means that the collection of all the measurable sets in Rn. Okay, so let's see the proof. So remember that we just need to show that for any t we have, for any test set t, I can show that this is greater than, the left-hand side is greater than or equal to the right-hand side. So this is the only thing that we need to show. Okay, so to show that, let's see that for any t, and let's look at the outer measure of t. And because this outer measure of t must be bigger than or equal to the outer measure of t, intersection of t and the E complement. The reason is the intersection here is a subset of the t. So the outer measure must be bounded by the outer measure of t as well. So this must be true. And then we can also show that this is equal to this plus this. And the reason is the second term I'm writing here must be 0. Okay, so this is because the mu star of t, intersection of t and E, must be less than or equal to the mu star of E. It's because the intersection here must be a subset of E, right? So that's why we must have, this is a subset of E. So we must have that. But on one side, I know that this measure of E is 0, outer measure of E is 0. And on the other side, I know that this must be greater than or equal to 0 because outer measure must be non-negative. So what this means is this term here must be 0. Okay, so that's why I only added a 0 here. I didn't change anything. This term is just this, which is 0. Okay, and now you can see we got this inequality. We show that for any test t, the outer measure of a t is bigger than or equal to the sum of these two. And according to the definition, as we showed, we just need to show this direction, but because the other direction is always true, so that's how we show that this this e must be measurable. So I don't care what this e is; it could be really complicated, but as long as the outer measure is 0, then this e must be measurable. Okay, so this is the a easy way to check if e is measurable, just as long as the outer measure is 0. Okay, so this is kind of a little bit trivial case, since the e is really special. It has a measure 0. Let's consider more general cases. Okay. A property of the outer measure is, suppose we have two sets, E1 and E2, be just two sets. Okay, they don't have to be not necessarily measurable. It's just two random sets. Okay. If there is a measurable set S such that the E1 is in S and the E2 is in the complement of S, that means this E1 and E2 can be separated by some measurable set S, then we can claim that the additivity of these two sets still hold. Okay. So in general, we know that this doesn't hold for arbitrary sets. We know that the outer measure, we must have this direction, but the other direction may not hold for outer measures. Okay. But if these two sets can be separated by a measurable set, then this will hold. Okay. The proof is very simple. We just let this t to be, the test set t to be E1 union E2. Then we know that the mu star of t should be equal to the mu star of E1 union E2, right? And this is equal to the mu star of, because S is separable, S is measurable, so we know that this E1 union E2, take this with S, intersection with S, plus this same set with S complement. Okay, so now let's first look at the first term on the right. Okay, this is the union of E1 and E2 here, and this is S. So remember that the E1 is contained in S, the E2 is contained in S complement. So that means the E2 cannot overlap with S, right? Because E2 is in the complement of S. So the union of these two together, taking the intersection of this and S, I can only take the effect of E1, right? So that's why this whole term is just the intersection of E1 and S. And as I said, the reason is E2 is in S complement. Okay. Similarly, let's look at this. The E2 is in S complement. The E1 is in S, so it doesn't overlap with this S complement at all. So that's why the intersection of these two sets is just the intersection of E2 and S complement. So that's why we have mu star of E1 intersection with S plus mu star of E2 intersection with S complement. But remember that the E1 is contained in S. So that's why the intersection of the two is just that E1. And similarly, for the second term, because E2 is in S complement, so the intersection of the two is just E2 itself. That's how we prove that this is just equal to this. Okay, so the additivity of the outer measure works on this union of E1 and E2. Although the E1 and E2 themselves may not be measurable, they still have this. Okay, so next let's study several properties of the outer measures. Okay, the first property is that empty set must be measurable. Second one is that if E is measurable, then the complement of E must be measurable as well. The third one is that if E1, E2 are both measurable, then the union of them, the intersection of them, and the difference of them, either E1 minus E2 or E2 minus E1, they are all measurable. And the last one is the countable additivity. If Ek is in M, is measurable for any K, then the union of them will be measurable. And moreover, if those E's are mutually disjoint, then actually the countable additivity will hold. That means the mu star of the union is actually the sum of the outer measures of each set, of all the sets here. Okay. So let's prove that. So the first one is really easy to prove because the outer measure of empty set is 0, right? And we showed before that any set with outer measure 0 is measurable. So the empty set must be measurable. Second one is that remember that if E is measurable, then for any test set T, it is equal to the outer measure of T, intersection of T and E plus the intersection of T and the E complement. But this term here is nothing but the complement of the complement. So in this sense, we can see that the outer measure of T can always be written as the outer measure of the intersection of T and the E complement, and the outer measure of intersection of T and E complement, right? So in this case, you can see that the E complement is also measurable. Okay, so this is easy to show. Okay, the third one. We first show that the union of E1 and E2 will be countable if both of them are countable. Okay, so to show this, for any T, remember that we still just need to show that for any T, this is the bigger than or equal to. We hope to get this, mu star of T intersection with E1, E2, plus the intersection of T and E1, E2 complement, right? This is the way we want to show. If we can show this outer measure of T is bigger than the sum of these two, then we can, for any T, then we can show this E1 union of E1 and E2 is also countable. Okay, so to show that, let's first use the measurability of the E1. Say, because E1 is measurable, so at least I know this. I know the outer measure of T is equal to the sum of these two. Okay, and this is because the E1 is measurable. Okay, next, we know that this first T intersection of T and E1, we can treat this whole thing as a test set. I can treat this whole thing as a test set and use decompose it using the E2. Okay, that means the first term here becomes the intersection of these two, and then E2 plus the intersection of these two, and this, right? These two together will become, this term becomes the sum of these two. And the reason is that we're using this as a test set for E2. Okay? Okay, but that's only for the first term. We can do the same thing for the second term, which gives us, let's again take this as a test set, and we know that it can be written as the sum of these two. Okay, so now let's take a look at what this actually means. If I have the E1 like this, I have the E2 like this, and I will have the T like that. Okay, so the first term here is the intersection of the three. So this is here. Okay, and the intersection of T and E1 will be here. And take the E2 part out. This intersection of these two is like the difference of this and this, right? It's just this side minus this side, minus this E2. So that's actually just this part. Okay, and similarly, you can see here you have the T intersection of T, E1 complement E2. So it's like you take the intersection of T and E2, which will be here, and you take out the E1 part. So you only have this part left. And finally, you have this. Okay, so I only care about I first cared about these three terms. I have showed that the three terms are this, and then this. So you can see what they are. They're the intersection of T and the union of E1 and E2, right? So because this, and this together is the intersection of T and the E1 union E2. Okay, so that's why this whole thing together is bigger than or equal to the mu star of T, intersection of T and the union of E1 and E2. Okay, just the three sets altogether become this set. So that's why by the subadditivity of outer measures, the sum of the three must be bigger than the measure of the union of them. Okay, so that's for the first term, first three terms. And the last term, I will just keep it in the following way, because I see that this is just the intersection of T and the intersection of E1, E2. But remember that this term, by the De Morgan's law, is equal to the complement of union of E1 and E2, right? So that's why this is just equal to the intersection of T and this complement of the union of E1 and E2. And the first term is nothing but, I just copy it here. So you can see this is the intersection of T and this set. This is the intersection of the T and the complement of the set. Right? So what we showed so far is that the outer measure of T is bigger than or equal to this plus this. And then by now we can see that the union of E1 and E2 is measurable. Okay, if we have this, then we can easily show the other ones, because the E1 intersection of E1, E2, according to what we showed earlier, is just equal to, by the Monaco's law, this is just equal to this. Right? And as long as we can show the inside is measurable, then we can show this is measurable. Because of the second item, we show that if a set is measurable, then the complement will be also measurable. So we just need to show this is measurable. If this is measurable, then the intersection must be measurable. But we show that if E1 and E2 are measurable, then these two must be measurable. The complements of them will be measurable, and the union of them will be measurable, as we just showed. The union of two measurable sets is still measurable. So this will be still measurable, and the complement will be measurable. That's why this will be measurable. Right? And also, the E1 minus E2 is nothing but the intersection of E1 and E2 complement. As we showed that if E2 is measurable, then the E2 complement will be measurable, and intersection of them will be also measurable. So this is how we show the three of them. Thus, these three of them are all measurable if E1 and E2 are measurable. Okay, we first show a claim. So my claim is that if E1, E2 are both measurable, and E1 does not overlap with E2, then the outer measure of E1 let's say more specifically, then for any test set, there is the outer measure of this T intersect with the union of E1 and E2 is just equal to the sum of these two. Okay. So the proof is actually very simple here. So first of all, we know that by distribution law, we can rewrite the intersection of T and this union as the T intersection of T and the E1 union with intersection of T and E2. Right? So that's what this term is. Let me move this here. So this is just equal to this union with this. Okay, so now notice that this is a subset of E1. This is a subset of E2, which is in the complement of E1. So previously we said that if you have a union of two sets, and the two sets can be separated by a countable set, then the sum of this, the union of these two sets will have the same outer measure equal to the individual outer measures. So here we have, this is contained in E1, and this is contained in E1 complement. That means these two sets are separated by the E1. So we know that the union of the outer measure of their union is just the sum of their outer measures. Just have this. Okay, so that's how we proved this claim. And this claim can be extended to more than two sets. So suppose I have E1 through the EK, they're all measurable sets, and the EI, EJ do not overlap for any I different from J, then for any test set T, there is the intersection of the two, which the intersection of T and the union of those EIs. It's just the sum of the outer measure of T, intersection of T and EI for I from 1 to K. Okay, so you can just apply the previous claim one by one. We'll get this. Okay, so what it says is if you have mutually disjoint measurable sets, then for any T, you take the intersection of T and the union. It's like you take the intersection of T and each one of them, and then you can get the measure of this total one as the sum of these individual measures. Okay, so we're going to use this claim to prove the item 4 here. So remember the item 4 that we first need to show that. So recall that our goal here is to show that if EK are measurable, then the union of them is also measurable, right? This is what we want to show. All right. So first of all, without loss of generality, we assume these EIs are mutually disjoint. Okay. The reason is if they are not disjoint, mutually disjoint, we can just define, say, the Fk to be Ek minus all the previous EIs. So for I from 1 to K minus 1. Okay, so this is everything in Ek, but not has appeared in the previous E's. Okay, so by defining the Fk in this way, we can see that every time the Fk just collects whatever new in Ek. So the union of Fk will be still the union of Ek, but the Fk's are mutually independent, are mutually disjoint. So the union of Fk will be the same as the union of Ek, and the Fk's are mutually disjoint, right? So we can, by this we can see that we can always assume that the EKs are mutually disjoint, since we just need to worry about their union. We just need to see If there are each one of them is independent, then I just need to show this, or equivalent I just need to show this is also measurable, right? So we can assume that they're mutually disjoint. Now for any test set T, we have I think we first define. Let me first define this. We denote the partial sum of the EKs as Sk. So Sk is the sum from E1 to Ek for any K. And also we define S to be the complete sum or complete union. Okay. Then for any test set, there is we know that the if each EI is measurable, then the finite sum is also measurable, because we have shown that the union of two measurable sets is measurable. If we take the union of finite many measurable sets, it will be still measurable, right? Just by extending the item 3 above. So we know that Sk will be measurable. So because Sk is measurable, we know that the measure of T, outer measure of T, can be split into two parts. One part is this, and the other part is the T with the complement of Sk. Okay, so now remember that the we said that we can always assume those EKs are mutually disjoint. So we have mutually disjoint sets, and because of the claim 2 above, we know that this first term is just the sum of the mu star of T and the EI for I from 1 to K, right? This is the second claim we just made. That's one. The other one is that the Sk is a subset of S, right? See our definition that Sk is just a partial sum, a partial union, and this S is the total union. So we have this, and that's why the complement of that contains the complement of S. And that's also why the intersection of this contains the intersection of T and S complement. And that's why the mu star of this left-hand side is bigger than or equal to the mu star of the right-hand side. So that's how we show that this is actually bigger than this, right? So we show that this is equal to this term, but this is bigger than or equal to this. So in total, we will have this bigger than or equal to that. Okay, now we can see that first let's say we do not consider the special case where the T has a infinite outer measure. The reason is if this left-hand side is infinite, then it will be bigger than or equal to the sum of anything, right? So it doesn't cause any issue. So the key here is that for any T with a finite outer measure, we still want to show that the S, the one here, is measurable. So far we know that this is for any test set with finite outer measure, we can show that this right-hand side here is a series plus a constant number, and both of them are non-negative. And by increasing K here, this first term gets larger and larger. So in total, this term is a non-decreasing sequence, right? It's a sequence of numbers that are non-decreasing, and it's bounded above, right? So that means this limit actually exists. We'll tend K to infinity. This one will have a limit. So the limit exists, and that's why and also the limit is also less than or equal to the left-hand side. So let k going to infinity, we have the outer measure of t is bigger than or equal to the infinite sum of mu star t and ek plus mu star of this. Okay, and on the other hand, we know that this union of this is equal to the sum of this individual outer measures is bigger than or equal to the outer measure of the union. So the union of these sets. Right? In the second term, we do not change it. But notice that this first term, if I use the distribution law, this first term is just t intersect with the union of k from 1 to infinity ek. So that's just the intersection of t and s. And that's why this first term is just the mu star of t, intersection of t and s. And the second term is the same. And that's how we showed that for any test set t, we will have this greater than or equal to this. And that means that the s is measurable. Okay, so the s as the union of those EKs is measurable. Okay, we can also show that the additivity, assuming that these EKs are mutually independent, we actually can show that the outer measure of S, in this case, we can just take S as a test set. Then we know this is bigger than or equal to the right-hand side, which is the sum from 1 to infinity mu star of t intersection with u1, so S. As we said, we're just taking t as S. So this will be S, this will be S. But this term will be just gone because it's just intersection of S and S. Complement, it has just empty set. So this is gone. So this will be just become this, right? EK will be just this, right? And you know that the intersection of S and EK, S is the union of all the EKs. So the intersection of these two is nothing but just EK itself. So we're just having this of EK. Okay. On the right-hand side, on the left-hand side, this is just mu star of the union. Okay, this is how we show that the countable additivity, if all those EKs are mutually disjoint, then the outer measure of their union is just equal to the sum of their own outer measures. Okay, so this is ideal. This is actually our original motivation. We said that the outer measure itself is not necessarily countably additive, but now, as long as we're focusing ourselves or restricting ourselves to the measurable sets defined earlier, then this mu star, the outer measure, will be countably additive. Okay, so now we can see that for previous claims, because of the previous claims we made, the additivity set is a measurable set. If set E is itself measurable, the complement of that is also measurable. And also show that if the EKs are measurable, then the union of them are measurable. So you have this tree, that means the M here is actually a sigma algebra. And this sigma algebra is the collection of measurable sets, and this M is actually called the Lebesgue measure, or the Lebesgue measurable sets. Okay, so that's the definition we're going to give. For any measurable set, the Lebesgue measure of this set E is defined by its outer measure. So we denote this measure as mu itself. That's just the mu star. Okay, and this mu is called the Lebesgue measure. In this case, the set or the space Rn and the sigma algebra M, and the measure is called the Lebesgue space, Lebesgue measurable space. Okay, so remember that right now the space needs to contain 3 components. The first is the space itself. Second is the sigma algebra, which is a collection of measurable sets, as we saw that's just M. And also for each element in M, or for each measurable set, we can get its measure, which is just the outer measure of the set. So that's the mu. Okay, so this is called the Lebesgue measure space. Okay, Lebesgue measure space of Rn. Okay. So we have lots of nice properties about the Lebesgue measure. So in general, actually, we can define Lebesgue measure on a general set. Suppose we have a space X, and then we have a sigma algebra of that, and the mu is called a Lebesgue measure if it satisfies the following 3 conditions. First, it is a non-negative. It takes a non-negative value. Okay, for any set E in the sigma algebra, it takes a non-negative value. Second is that the empty set has a measure 0. The third one is that the mu is countably additive, and that's the same as before. By countably additive, we mean this if these EKs are mutually disjoint, then the measure of this union is equal to the sum of these individual measures. Okay, so in this case, we can also construct a Lebesgue measurable space. So this X doesn't have to be the Rn, but we only focus on the n-dimensional Euclidean space in this course. Okay, and in particular, we call this set we call this space finite if the measure of X itself is finite. Okay, so let's say. So we call X mu is called finite if the total measure of X is finite. Okay, but this is a rather special case. We use this only for the last chapter of this course, but in general, we say that this is called sigma finite. If we can show that this X can be written as a union of countable sets, and for each of them, it is finite. Okay? So that means if X can be written as a union of countably many sets which are all finite, which all have finite measure, then we call this X sigma finite. Okay, or we call this measure as sigma finite. Okay, next we show a useful property of the Lebesgue measures. Suppose we have a sequence of measurable sets, and they are non-decreasing. Then the measure of this limit is also equal to the limit of the measure of the individual measures. So remember that the limit of this is just the union of the EKs, right? Because these sets are non-decreasing. So we know that this is also a measurable set. And what we're trying to show here is that the measure of this union is equal to the limit of the measures. Okay, so to prove this, we first can see that if the limit of this mu ek is infinity, then we know that this right-hand side is infinity, then the left-hand side must be also infinity. The reason is this is bigger than or equal to the individual one, and we know that this is increasing. So this is actually an increasing sequence, and it has a limit. But if the limit is infinity, it's approaching to infinity, then this, since it's always bigger than that, then the left-hand side must be infinity as well, right? So if this is infinity, then apparently this mu of limit ek is also infinity. Okay, so there's nothing to prove. So assume now that I'll consider the case that this is not infinity, it's actually finite. Then first we can see that the limit of ek, as we just mentioned, this is always bigger than or equal to the individual one. The reason is, as we said, it's just the union of the EKs. So it must contain each individual EK. So that's why the right-hand side must be less than or equal to the left-hand side. And then this also implies that this is bigger than the limit of mu ek. Okay, and not only that, we can actually define, let's say D naught to be empty set, and dk to be ek minus 1. Okay, so remember that this sets are increasing, so this is ek minus 1. This will be the ek. So the dk will be just this area, right? This area, the ring area. Okay, but we can look at it. Notice that this union of the ek, which is just the limit of ek, is equal to the union of the dk's. Okay, since we dk collects all the differences between them, so you take the union, it will be still the original union of EKs. And not only that, we can also see that the decays are mutually disjoint. Right? Also, we can see that the limit from 1 to infinity. So we have a countably many mutually disjoint sets. So this is just equal to the measure of their union, and we said this union is just the union of k. Okay, and now I can see that this is also just let me see this. See, in this way would be better. For each finite k, we'll have the mu of ek is equal to the mu of the union for di for I from 1 to k, right? Because the di accumulates the differences, and this is just equal to the sum from 1 to k of di, because they are mutually disjoint. And we know that the limit of this is finite. So that means the limit of this is finite. So this implies that this is equal to the limit of the EKs, and that should be finite. Okay, now we find something interesting. Here we have an infinite sum, or it's a series, and that's a finite. That means this thing will get closer and closer to zero. We must approach to zero, right? Because the series is finite. Okay, that means for any epsilon, there exists k large enough such that the sum of k from capital K to infinity of this mu di or dk should be less than epsilon, right? So the tail must be arbitrarily small. Okay, for any epsilon, the tail can be smaller than this epsilon for the capital K large enough. Okay, now we are ready to prove the main inequality. We have shown that this is greater than that, and to show this two are equal, we just need to show this is also less than that. Okay, so let's see why that's true. What we want to show is the left-hand side is also smaller than or equal to the right-hand side. Okay, so this is equal to, as we said, it's just a union of those EKs. Right? And we show that this union of the EKs is the same as the union of the DKs. And this is just equal to the sum of the measure of the DKs, because the DKs are measurable and they are mutually disjoint. So that's why, because of the countable additivity of the measure mu, we know this last inequality holds. And this last one, as we showed, this is the finite, right? This is the finite number. So that means I can rewrite this. I can rewrite this as k from 1 to capital K minus 1 of mu dk plus the tail, which is little k from capital K to infinity of mu dk. And we said that for any epsilon, we can choose this capital K large enough such that the second term is less than epsilon. So this will be less than or equal to the first term plus epsilon. The second term is just bounded by epsilon, right? And then this first term can also be written as the mu of the union for dk from 1 to k minus 1. And then we know that the union of that is nothing but just the ek minus 1, right? and plus epsilon. So what we have showed so far is that for any epsilon, this is less than or equal to this plus epsilon. So that's why the limit of the left-hand side, the left-hand side will be less than or equal to the limit of the right-hand side for k tending to infinity. So it will be just less than or equal to this of mu ek plus epsilon. Okay, for any epsilon we can show this, and this implies that we know that the left-hand side, mu of the limit of the sets, is actually just less than or equal to the limit of the mu ek. Right? So now we have two directions. One direction is trivial to show that the mu of the limit is bigger than or equal to the limit of the mu's. And on the other side, we show that the mu of the limit is less than or equal to the limit of the mu's. So these two together implies that the two actually are equal. Right? These two are actually equal. Okay, so now let's see what we actually get here. We show that if we have a non-decreasing sequence of sets, of measurable sets, then we can exchange the mu, the measure, and the limit. Okay, so taking the measure of the limit is the same as taking the limit of the measures. This is what the claim made. Right, this is what the theorem says. A corollary of this is that if each ek is measurable and the E1 has a finite measure, okay, we require E1 to have a finite measure. So this is different from before. We require this to be finite. And also the E1, E2, they are decreasing. Then this implies that the limit of the ek, the same conclusion. It's the measure of the limit is equal to the limit of the measure. That means the limit and the measure can exchange order. Okay, the proof of this is just applying the previous one. Notice that we have this mu1 is finite, so it's just a constant, it's a finite number. We take the difference of this, by the way, I should first say that because this first E1 has a finite measure and this is decreasing, so the later ones also have finite measures, right? And then we can define or denote the Fk to be the E1 minus Ek. And because the Eks are decreasing, so the Fks will be increasing, right? The first Fk, the F1 should be empty, the F2 should be E1 minus E2. Okay, F3 should be E1 minus E3, and it's increasing. So I know that the F1 is empty, and the F2 will include F1 and include F3. So the F actually are non-decreasing. So it's increasing that we can apply the previous claim. So how we're going to use that is here. When we look at the measure of mu1 minus the limit of the measure of Ek, we know that this is just a fixed constant. It's finite fixed constant. And then in taking the limit of this should be equal to the limit of the measure of E1. I can put this E1 into the limit. I have this. Right? And this is just the limit of mu of E1 minus EK. The reason is the E1 contains EK, so that the E1 can be decomposed as the EK and the E1 minus EK. Right? So this is the union of this and this, and these two are mutually they're disjoint. So this right hand side will be equal to just the Fk according to our definition. And now because Fk is increasing, so according to the previous theorem, this should be equal to this. Right? And then we can see this right hand side, the f of the limit, the mu of the limit is just equal to the union of them, because this is increasing. Okay, and according to our definition of the Fk, this is nothing but just the E1 minus EK. But let me rewrite this as E1, intersection of E1 and EK complement. So that is equal to the mu of, I use the distribution law, this is just E1, and the intersection of the union of the EK complements. And that's equal to the mu of E1. Using the Lebesgue law, this is just the intersection of this EKs, the complement. Right? And then this is like, because it's the intersection of E1, a complement of something, so this is just equal to mu of E1 minus the intersection of those EKs. But remember that these sets are decreasing. So that's why this is just a subset of that. And that's why we can rewrite this as just the mu of E1 minus the mu of this intersection. Okay, and finally, this right-hand side is just a mu of the limit, because the sets are decreasing. So the intersection of them is just the limit. And now we can see that both sides have this mu E1, so we can cancel this. And then what's left is just the limit of the mu is equal to the mu of the limit. Okay, so the limit of the mu EK is just equal to the mu of the limit of EK. Okay, so here notice that this is just the same as the previous theorem, except that we do require the limit, the mu1 needs to be finite. Actually, it doesn't have to be the mu1, it can be any middle ones, say EK. Starting from some EK, the measure is finite, because the limit it doesn't matter what happens in the first fundamental terms for the limit. But we do need this to be finite for some EK. The reason is, remember that we need this to be a finite number to actually put this inside, right? So this is where we actually use it. And in practice, that's indeed, we can find a counterexample if the E1 is not, or the E1 is not finite, or any of those EKs are infinite, then we actually may not have this claim on the right hand side. We probably will not have this if all of those are infinite. So for example, say we have this R, the set of real numbers, and we define the EK to be, say, the open interval from k to positive infinity. So now you can see that none of those EKs has a finite measure, right? And the intersection, so the EKs indeed are decreasing. As you can see, the EKs, we do have the E1 that includes E2, includes E3, so on and so forth. So the limit of the EK is the intersection of the EK. But as you can see, the intersection of those intervals will be just empty. It will not include anything, right? Because it doesn't matter how large this number is, and for k large enough, k larger than this number will not be in EK anymore. So it will not be inside the intersection of all those EKs. So that's why this means that the measure of the limit will be equal to the measure of the empty set, which is 0. But on the other hand, mu of EK itself is infinite. So this means that the limit of this mu EK, because each one is infinite, so this whole thing is just infinite. So that's how we can see that this is not equal to this. Since one is 0, the other one is infinity. Okay? So that's why the finiteness is important here for this decreasing case. But it doesn't matter in the previous theorem. If it's increasing, that doesn't matter. The worst case is that they're both tending to infinity. Okay? But this will always hold. You can exchange the limit and the measure. But for decreasing case, remember that you should have at least one of them to have finite measure for this exchange to work. Okay, let's take a look at an example. Suppose we have a sequence of measurable sets, and the sum of these measures is finite. Then we can claim that the upper limit of these sets has a measure 0. Okay, to prove this, let's first recall what is the upper limit. The upper limit EK is just the intersection for j from 1 to infinity, and then the union for k equal to j to infinity of this EK, right? So this the upper limit of the sequence means that it contains the elements which are in infinite many of those EKs. Or in other words, for any j, there exists some EK, there exists some k such that the element is in EK, right? This is what we learned in the first lecture. Okay, so now let's take a look at this set. We can call this Bj. Okay, so what can I say about this Bj is that if j is increasing, then this Bj is getting smaller and smaller, right? So the Bj actually is decreasing as j increases, right? Because we're taking the union of fewer sets. So define the Bj to be the union of EKs for k greater than or equal to j, then you can see that the Bj is decreasing, right? Or in other words, B1 contains B2 contains B3, right? This is what this means. Okay, and on the other hand, we also can see that the B1 is equal to the mu of of the union of everyone, and this is less than equal to, so we said this is less than equal to the sum mu of ek, because this ek is not necessarily mutually destroying, so we don't know if it's equal, but at least we know it's less than equal to this, and this is finite. Okay, now we have bj's that are decreasing, and the first b1 has a finite measure, so we can apply the corollary above, and that means we can get that the limit of this, let's say in the other word, another direction, that the limit of those bj's should be equal to the measure of the limit. Right? And remember that the bj are decreasing. The limit will be just the intersection of those bj's. Okay? And then we replace the bj. We know that that's actually just the upper limit of the ek's. This is just j from 1 to infinity, union of k from j to infinity of ek. And this is just the upper limit of ek. Okay, but on the other side, we know that this mu of bj is equal to the mu of the union for k from j to infinity of ek, right? And this is less than equal to the sum for k from j to infinity of the measure of ek. And remember that this series is finite. So the tail must be approaching to 0 for j tending to infinity. Right? The tail must go to 0 as j goes to infinity. And in other words, the limit of this mu of bj should be equal to 0. Okay, and now we show that on the one hand, the limit of bj should be equal to the mu, the measure of the upper limit of ek. On the other hand, we show that the limit is equal to 0, and that's why we claim that this is just equal to 0.